All right, so the directional derivative and gradient. All right, so if you think about gradient in like everyday language, you might be thinking about like the grade of a three-dimensional surface, like kind of like the slope of a three-dimensional surface. You know, if I were to say, oh, what's the gradient of that hill? Most people are probably going to be thinking, you know, something along the lines of slope, right? And so that's not incorrect, but there's more to it than that, right? So there's all this stuff about the objective, but we have this component here. Okay, that was supposed to be a box, and that didn't end up being a box. All right, let me make it look all box-like. You know, that's a good enough word of the day. We'll start with that. Box. Let's see what you come up with. All right, let the function f of x comma y be the height of a mountain range at each point where x is equal to x comma y. Right? If you stand at some point x equals a, the slope of the ground in front of you will depend on the direction in which on the direction you are facing. It might slope steeply up in one direction, be relatively flat in another, and slope steeply down in yet another direction. Right? So that's kind of starting to get the idea across related to multivariable functions. So just kind of going back, it might be a little ways. I want to find that terrible diagram I drew. This bad boy, where, and this was when we were talking about extreme and saddle points for the first time. It was the idea that from one perspective, the maximum might be the highest point, or I'm sorry, the maximum is always going to be the highest point, but a point might appear to be the maximum, but from another perspective, a point might appear to be the minimum. Right, the gradient takes that into account. Right, the idea that depending on where you are in a surface or on a surface, you're going to have different perspective related to the slope. Right, partial derivatives of f will give the slope. Okay, so partial derivative notation in the positive x direction and the slope in the positive y direction. Right. So that's what we're getting when we take the partial with respect to x and y. We're getting the slope in the positive x direction and the positive y direction. We generalize this to calculate the slope in any direction. We call that the directional derivative, right? And so we rely on knowledge of what that direction is in order to know what the slope is, in order to know what the derivative is in that direction. But we will be able to make a determination of what that slope is as long as we know which way we're headed, right? So it's kind of like you just visualize yourself standing on the side of a hill, you know, like it's very, you know, somewhat steep hill. That hill is either going to be a steep climb up, a steep walk down, or a relatively flat walk in an orthogonal direction, right? So if you're kind of going against the grain, if you will, then it won't be that challenging at all. Yeah, maybe your ankles will hurt afterwards, but yeah, you're not going to exert yourself by fighting off gravity the way you would by going uphill. All right, so it will depend. Now, I know that when you're running, for example, I mean, I used to do this back when I was not sedentary, but when I would run like through the woods, and you know, even when I'm skiing, like the same principles hold. If you're on the side of a hill and you want to maintain an even path going on that side of the hill, you don't just run or ski straight, because gravity and the grade of the hill is going to take you downward. All right, that's actually your directional derivative. The rate of change is going to drag you in the negative direction. Right. What you do is you aim yourself in an upward direction so that you're corrected onto the level path. right? You make those little minor course corrections as you go so that you're constantly staying on that path. And most of us, especially if you're running, jogging, whatever, walking, you don't even realize you're doing it. But if you're skiing, you absolutely realize you're doing it. Because it's like, oh, why are you aiming your skis uphill? Well, because I want to go straight. That doesn't make any sense. Okay, well, then aim your skis straight and see what happens. Right? So that's kind of along the lines of what's happening here, except we're doing the math line. Right? So the model, very straightforward, just it's a hideous in terms of the notation, but it's the first order partial with respect to x at some point AB multiplied by the component of u, the x component of the unit vector u, like u as in the unit vector, plus the first order partial with respect to y evaluated at some point AB, some known point. And you see in the example to follow, there are defined points related to that unit vector. Again, the appropriate second component of the unit vector, right? So find the directional derivative of each function in the given direction, in the direction given by the angle theta is equal to pi over 4. All right, so first off, very simple, not always simple, but in this case simple, f sub x, 2x, f sub y, 2y. All right, now we're defining u as any unit vector. Right? So if I'm telling you that the directional derivative related to the function f at some point AB, but I'm going to leave it as xy right now, just so I write it in general terms or more general terms, is going to be 2x multiplied by whatever u sub 1 is plus 2y multiplied by whatever u sub 2 is, right? Because essentially it's the dot product between the first order partial vector, which we'll get to in a few minutes, and the unit vector. We're going to have to come up with u1 and u2 somehow. So let's take a step back and see what that's all about. Unit vector in any direction. Well, we learned about that. Unit vector in any direction, u would be equal to cosine of theta comma sine of theta. So that actually tells us that u sub 1 is cosine of theta and u sub 2 is equal to sine of theta. But then it kind of begs the question, well, where's the sum business coming from? Well, if I take f sub x comma f sub y and dot that against u sub 1, u sub 2, I would actually get this linear combination, right? So f sub x, u1, f sub y, u2 added together, right? So the directional derivative is actually the dot product between the unit vector and the rates of change associated with the original multivariable function, right? So where does that come from? That's all part of the story, right? So it's coming. I got a bunch of proofs that we're going to be working through, and all your questions will be answered. Right? So 2x, instead of u sub 1, I can now say cosine of theta, plus 2y, instead of u sub 2, I could say sine of theta. All right. And again, that's the directional derivative in the direction of some unit vector u for the vector multivariable function f sub xy. Now, I want to get more specific. It's the unit vector in the direction of pi over 4. So d sub pi over 4, also knowing that we're working with this at 2 comma 1. So 2 times 2 cosine pi over 4 plus 2 times 1 sine of pi over 4. All right. So by dotting the first order partials with the unit vector, we're actually going to get a scalar quantity. That scalar quantity is going to be the derivative or the rate of change for the function going off based off of that angle of theta equals pi over 4, but also assuming that we're standing at the point 2 comma 1. Right, so let's see how that shapes out. We're looking at 4 times radical 2 over 2 plus 2 times radical 2 over 2. Clean it up. 2 radical 2 plus radical 2 is 3 radical 2. No, barring any catastrophic error. Right, so what we just got is the rate of change for this multivariable function. Now, what is this multivariable function? Well, it looks like the equation of a circle, but it's not, because it's z equals x squared plus y squared. So it's z as in a variable z is equal to x squared plus y squared. That still has the characteristics of a circle centered at 0, 0. But now I'm saying that depending on the value of z, I could have a different radius. So what we end up with is a circular paraboloid. But let me show you specifically why that ends up being the case. And then also how this all kind of plays out. I think, yep, I did see it. Shocking. How about this? I never want to recover the changes, ever. So z equals x squared plus y squared. All right. So what I'll do is I'll just put in a z value, for example, of 1, z equals 1. Now, it's kind of hard to see. It always is hard to see, but if you change the perspective, it gets a little bit easier. You could also change the color scheme to make it a little bit easier to kind of get a good view. Like changing the opacity tends to help some. All right, that little shadow inside, which is, I probably could have benefited from going a little bit more opaque here. Not too opaque. That's kind of, honestly, this will work. I'll just live with this. So we have the intersection between this plane and the ghost of the paraboloid. And you can see that intersection is forming a circular path. Now it's a circle with a radius of 1 because the z value is equal to 1. Now if I let z equal, let's call it c. Let me actually delete the function first, type it in again. And sometimes it gets annoyed when I try to. All right, let's do it this way then, c. I wanted to create a slider, but it's being difficult right now. So let me just do it at 2. You see it moves up. It's got a bigger radius, specifically a radius of 2. So my ghost paraboloid, circular paraboloid this time, is intersected by a plane with a z value of 2. And the cross section is a circle with a radius of 2. So I'll make it 1.5 just to really drive the point home. All right, so z value 1.5, radius 1.5. Right. Now, if I plot the point 2, 1, and that would be 4 plus 1 is 5. So 2, 1, 5. That's going to be a point that's kind of floating out in space. Let me just kind of back it up a little bit. I will have to make it a little bit darker now. Oh, now it's not letting me do the, oh, because I'm on the point. Now it won't let me, lovely. Oh, I can maybe do it here. Settings, color. A little bit better. It's still kind of hard to see that A is actually going to be supposedly a point on that curve, the surface. It just keeps kind of moving. It looks like it's kind of off the edge, but it's really on there. It just doesn't look like it. You know, it's pretty awful, but that's the idea. What this is saying is now if I take this curve, so red is X and green is the y-axis. If I follow this surface moving in the x direction or the xy direction of pi over 4, right? So I'm actually going to follow the direction of y equals x. So if I follow this path, that's going to intersect the surface of the curve, the surface forming a curve, right? At that point, what I would be doing is following the path that's generated by the intersection of that plane created by y equals x. If I follow the surface starting at that point in the positive x, positive y direction, which generally in this case means going up, this is what the rate of change would be, right? In units per unit, you know, feet per second or whatever it happens to be, right? There's no reason to think that this is velocity or anything along those lines, but if our units for x and y are both, you know, feet, then it would be feet per foot or something like that, right? But then this gives us the slope at that point related to the intersection between that greenish looking plane and the paraboloid moving in the positive x, y direction, which because an increase in x and an increase in y related to this function leads to an increase in z, we can assume that means it's going up. This is a slope of 3 radical 2 in that direction. All right. So there's a lot of interpretation going on. This this I think is very reliant on having a good, strong grasp of the visual. But in the absence of that, a good, strong a grasp on how to create the visual if you can't create it in your head. Okay? Because even when I first started teaching this course, there were some moments where, I mean, x squared plus y squared was pretty easy, but there would be some moments where it'd be like x squared plus 2y squared plus, wait, is that an ellipsoid that's wide or is it tall? Like, which one is that? You know, so sometimes even for me, it's a matter of like, let me get that in GeoGebra and have a look at it. All right. And so it's pretty typical when it comes to that sort of thing. So number 2, put a star on that because it's just kind of rehashing what we just talked about, just with a different function. In fact, because it's still at pi over 4, the only things that'll be different would be your f sub x, f sub y, which will impact these guys. It's still at the same value, same x value of 2, y value of 1. Those are the same substitutables. So there's really not so much there, right? Now the gradient vector, this is kind of the natural follow-up to this. And I already kind of stole my own thunder a little bit in the sense that when we had the function written here, the du f x comma y, and I wrote it in terms of x and y rather than putting in the numerical value, that was more along the lines of the gradient. But even before that, when I wrote a vector that had just the first order partials in it, what we were getting was the gradient vector. All right, so that's actually the definition of the gradient vector. It's a vector that's made up of the first order partials. Depending on the type of function, if it's a two variable function, 3 variable function, 5 variable function, however many variables is however many components would be in the gradient vector. All right, so that part should be pretty easy to understand. It's just like what we've been talking about all along. It's what on earth we're going to be doing with this stuff and why we use it, what we use it for, how do we know when to use it and when to use some other technique. That's what makes this stuff tricky, right? And again, at the risk of sounding like a broken record and maybe even starting to piss people off, it's all coming, right? All the answers you see. So I'll read the blurb here, just because honestly, between this blurb and the one I highlighted on the previous page, I gotta say it was like probably like 3 or 4 semesters of me just hand waving my way through directional derivative and gradient and just hoping people understood what the hell I was talking about before I came across a website that did a better job of explaining it than I ever could, only because they started talking in terms of mountains and uphill, downhill, and stopped talking in terms of math. And I was like, you know what? I should have done that years ago. So I kind of like this blurb, so that's why I'm going to read it to you rather than letting you read it on your own. And I'm going to put a little box around it. All right, in most cases, there is always one direction u where the directional derivative is the largest. This is the uphill direction, typically. In some cases, such as when you're at the top of a mountain peak or the lowest point in the valley, this might not be true, of course, because, you know, like even though the direction in which the derivative is the largest, and remember, don't ever forget, derivative is rate of change. Derivative is slope, right? So there's always the potential to have a derivative, even though you may not necessarily make use of it, right? So when I say, or when this individual said, and I just copied it, in some cases, such as when you're at the top of the mountain, this might not be true. It's not that there's no slope there. It's just that you're already at the top. There's nowhere to go. You're already you've already reached the apex. Right? Let's call this direction, the direction of maximal slope. Both the direction m and the maximal directional derivative are captured by something called the gradient. All right, and it's denoted by this upside down lambda, which honestly, I've been told over the years, and I've read it everywhere, that it's pronounced that it's this upside down triangle. They call it nabla, but it sounds way too close to something that's like utterly horrific. That is what I just said is the one and only time that I'm ever going to say it. It's upside down delta from here on out. Right? There's a proper name for it, but it's way too close to something very, very horrible. And so, I'm not even gonna go there. Now, the gradient is a vector that points in the direction of m and whose magnitude is the directional derivative, but is the maximal directional derivative. Right. So the question becomes, well, how do you find the maximal directional derivative? Right. So the gradient is the vector that contains all the first order partials. Now you can write it in whatever form you want. You can write it as, you know, the f sub x. You can use the delta notation. You could write it in component form. You could write it in ijk notation. That's up to you. We know that if we want to find the directional derivative, we're taking the first order partials and dotting it against the unit vector. Right now, that unit vector cosine theta comma sine theta, yeah, that's wonderful. But we could also use the alternate definition of the dot product. Right? So we talked about this way back when, first unit, that the dot product is when you multiply. I mean, the obvious thing is when you multiply the components and add them all together. But there is an alternative relationship that defines the dot product as the product of the two magnitudes and the cosine of the angle in between them. Right? So you kind of start thinking about, well, what that might mean. And that's a geometric derivation that we'll get into. Right? But that's really important because we know that the magnitude of the unit vector has to be equal to 1. By definition, it's a unit vector. So then the directional derivative, the maximal directional derivative, it's been a while since it crapped out on me, so it's kind of only a matter of time. Is it going to at least bring me back to the right page? Of course not. Why would it? All right, so maximal directional derivative is going to be related to the magnitude of the gradient multiplied by the cosine of theta, assuming only if cosine of theta gives the largest value. So we would want to be thinking about what kind of theta value would allow this product to be the largest that it could possibly be. All right. So then you start getting into your unit circle knowledge. All right. So you think about in a cosine function. And actually, unit circle, yeah, that's true, but you could even go more basic than that. You just think about an ordinary cosine function, y equals the cosine of x. You just think about the largest possible cosine value that you can get as a result, right? It oscillates back and forth between a -1 and a +1, right? So cosine is its largest when theta is equal to either 0 or 2 pi or 4 pi or anything that's coterminal with that. You know, maybe a -2 pi, right? So if cosine is equal to 1, then du f of AB is at a maximum. If cosine is equal to -1, it's at a minimum. Right? So it'll be a maximal derivative, directional derivative, but only if the cosine value is equal to 1. So you think about, well, when does that happen? It happens when you're going in the direction of 0 degrees, 0 radians, or 2 pi radians, or 360 degrees, etc. Right? So that's where all these properties of the gradient come into play. The maximum rate of change occurs in the direction of the gradient, but specifically when theta is equal to 0 degrees, right? The minimum rate of change happens in the direction opposite of the gradient, and that is when theta is equal to 180 degrees. Now, I'm also kind of implying here that it's anything equivalent to those, because, you know, when you're dealing with periodic functions, that's just how it works. You know, it's not just a matter of 0 degrees and only 0 degrees, 0 degrees and 360 degrees or whatever, where appropriate, all right? So all of this stuff holds true, but it all has to do with our knowledge of the dot product. So again, we have to get back to the idea of, well, why would the dot product be appropriate, right? So anything else is going to fall into a category that's not necessarily a maximum or a minimum. The rate of change is 0 in directions orthogonal to the gradient, and the gradient is orthogonal to the level curve, which we haven't talked about yet. F of xy equals f of ab. We'll get to that next class. Right? So that last one we have to sit on, but the first three we can actually kind of navigate through. In the case of the examples, or in the cases below, and in fact even numbers 3 and 4 on the next page, it really is very simple. If you want the gradient, all you have to do is find the first order partials, just making sure I didn't botch that. Sometimes you do things too fast, you as in me. And because of that, you pay the price. I think they're good though. Right, so the upside down delta, or the gradient, so again, we're just looking to compute the gradient in terms of xy. Pick your favorite notation. If it's a vector valued function, I'm more inclined to go with the component form. That's just a me thing. The magnitude is the same. It's the same way you find magnitudes of any other vector function. You square each part and put it all together, right? But the thing is, they could ask us for the direction of maximum increase, direction of minimum increase, you know, where it's a rate of change of 0, things like that. So this is really just kind of like the first step along that path. I'm going to put a star on this so I don't forget. Right, so we square each part. And pop a root over the whole thing. And if you find any advantage in simplifying this, then you go to it and take care of that. But I'm looking at this and I see, even if I were to square some things and factor some things out, there's no way I'd be able to really clean it up in a way that I would want to. So I'm just going to leave it as is, right? So if I happen to know the values of x and y, then what I'd be able to get from this is the rate of change, the maximum rate of change or minimum rate of change, depending on that particular point, you know, where I am. Right? Then I could go through the process of trying to solve for something like for example, if I wanted to know where what direction I'd have to go in order to have a rate of change equal to, let's say, 2. Then I would want to get my directional derivative computations involved and solve for the value of theta. But that's not what this is asking for, right? So whatever this yields after a substitution of x and y would be the maximum rate of change depending on whatever x and y are, right? So I'm going to pop a star on the next couple of problems, so numbers 3 and 4. 4 looks like it would be just a nightmare. It actually cleans up beautifully, but it starts off kind of like a nightmare. You do a little bit of writing early on and you think to yourself, there's no way I'm doing this the right way. And then all of a sudden it just starts cleaning up beautifully, right? So just keep that in mind if you start trying to tackle number 4, right? So just a little preview. Next class, we're going to talk about contour plots a little bit. There's not much we're going to do with that because I've already given you a little bit of a teaser on that. It used to be back in the day a big topic because we didn't have the technology that allowed us to see cross sections of 3-dimensional graphs very easily. So we had to draw them out. But now it's just hey, look at this animation I came up with on GeoGebra. And then it's like, oh, okay, cool. Moving on, so we'll tackle that pretty quickly. But I also wanted to get into a couple of contextual problems. They're kind of interesting, barring any typos. These are fresh new problems that I included since last semester. So they got to go through the quality control process to make sure that I didn't type them in incorrectly. But then after that, we're going to get into the intro for partial integration. And so if you're trying to get a sense of where this unit is going to end, we're looking at getting up to page, let me just make sure that I'm not lying. Yeah, up to page 71 before it's all over. All right. And it sounds like a tall order, but we're going to get there. The partial integration stuff isn't too crazy, at least the stuff that we're going to do in this unit. So I wouldn't be too concerned about that. It's like if you understand partial derivatives, then you're going to understand partial integrals just fine. It's just the applications of it, just like with partial derivatives, the applications are always going to be the tricky stuff. But that's more for unit 3, right? So yeah, just a little bit of a taste of what's to come. Not a whole heck of a lot more, but I didn't want you to be wondering, right? So at this point, I'm going to stop the recording.